Good afternoon, everyone. I am Rrezarta Krasniqi, an assistant professor at the University of North Carolina, Charlotte, and I'm excited to talk to you today about the open challenges in applying natural language processing to non-functional requirements. This is a critical area in requirements engineering, and we'll be focusing on semantic soundness problem, ontology generalizability, and model output interpretability. As you might know, NLP has made significant advancement and is used in various domains, from information retrieval and sentiment analysis to machine translation and question answering. And therefore, NLP is transforming how we interact with the language, and this highlights sort of NLP's versatility. So why is integrating NLP into the NFR domain so important, you might ask? Well, NFRs demand precision. We need NLPs to make accurate decisions. However, we face challenges. First, the semantic soundness problem. Semantic soundness in NLP pertains to the model's capability to accurately understand and interpret the meaning of words, phrases, and sentences in natural language. NFRs need precise meaning, and therefore improving NLP semantic soundness is essential when analyzing intricate safety-critical systems or regulatory documents. In addition, challenges in semantic soundness frequently arise due to word ambiguity, polysemy, or inconsistencies stemming from the terminology. Second, ontology generalizability problem pertains to the adaptability of NLP models across various domains and contexts. From an NLP perspective, these models are frequently tailored to a particular domain or subset of domains. They provide pre-trained word embedding, specific terminologies, or vocabularies that may not be applicable in many disciplines. As a result, NLP models often lack the necessary semantic knowledge and understanding to be effectively used within the NFR domain. And lastly, the NLP output interpretability problem. And this pertains to the extent of transparency in the decision-making process computed by NLP models. Now, the black box nature of some NLP models can erode trust and raise accountability concerns when used for important NFR decisions. For example, safety standards for self-driving cars are stringent. If NLP models predict issues related to sensor data, additional interpretation might be necessary to ensure the safety of passengers. But the lack of interpretability can lead to a lack of trust among the stakeholders, including end users, architects, developers, and safety operators. And this lack of understanding about how these models arrive at specific outcomes can question human confidence in relying on them. And therefore, we need to understand how NLP makes decisions. So this brings us to the core research question that we pose here is, what are the key challenges in using NLP for NFRs regarding semantic soundness, ontology generalizability, and model output interpretability? Let's start with semantic soundness. Consider the NFR, the system shall ensure high security for financial transactions. What does the term high security really mean? NLP models can grasp this. High security could involve encryption, authentication, data confidentiality, and the list goes on. And this ambiguity is a core problem. Here's another example highlighting the subtlety of semantic soundness. We have here two requirements. The first one is labeled as R1, and it says the product shall preclude personal data from being printed. And the second requirement, labeled R2, says the system shall grant the user to print the invoice summary. Now, a requirements analyst might look at these and say, well, they're both about printing, and groups them together. But semantically, they're quite different. R1 is about security and preventing data leaks, but the R2 is purely functional, printing an invoice. Now, NLPs can sometimes miss these crucial distinctions because they focus on keywords rather than deeper meaning. Let's consider another requirement in a very critical domain such as healthcare. Here, the medical diagnosis system should accurately identify rare diseases based on patient symptoms. In this case, semantic soundness is paramount. If the NLP model isn't precise, it can lead to misdiagnosis. Rare diseases are particularly challenging because their symptoms can overlap with more common conditions. So the NLP models often use distributional semantics, which is analyzing patterns in patient records to find clues. But this isn't always enough to differentiate between similar conditions because of the complexity of the data. Let's look at another challenges in semantic soundness, this time related to performance. Consider the NFR that says the website shall have low latency response time during high traffic events ensuring smooth user experience. The problem here is that the requirement implies slow response time, but it doesn't explicitly state it. The NLP models often struggle with this kind of inferred meaning. The diagram here illustrates the different components that contribute to latency, such as network time, client time, internet delays, and server time. To truly understand this NFR, the NLP model needs to grasp these underlying factors. This NFR in particular isn't just about speed, it's about handling high traffic efficiently to maintain that speed. So the NLP model needs to be able to interpret user feedback or performance metrics to identify when and where response time issues are occurring. Now let's shift to ontology generalizability problem. Here's an example of an NFR from an e-learning domain, and then this NFR says the system shall support personalized learning experiences for students. To do this platform needs to understand each student's needs and how they learn best. This is difficult for current NLP models. They often lack the deep knowledge of different subjects and teaching methods to truly personalize learning, so they fall short in adapting to individual learning styles. And finally, let's discuss the model output interpretability problem. Consider an NFR that says the virtual assistant shall respond to user commands accurately and with high speed, ensuring real-time interactions. Here, the NFR, the real-time response, is closely linked to what the assistant does, setting reminders, controlling devices, but it becomes hard to see how the NLP model decides which tasks to prioritize or why it responds in a certain way. This lack of interpretability and transparency is a problem. So let's discuss another example of the NFR that says the chatbot shall ensure data privacy and compliance with financial regulations while providing seamless user interaction. In this scenario, the financial chatbot, data privacy and regulatory compliance are tightly linked with functional requirements. Data privacy and compliance constraints make it more complex for NLP to handle customer queries. Existing NLP models, even traditional ones like random forest, lack transparency in their decision-making process. If a customer asks the chatbot to translate funds, the NLP model must ensure the transaction is executed securely and in compliance with financial regulations. Now, the lack of transparency in how the NLP model handles such requests makes it difficult to verify if data privacy and compliance are being adequately addressed. Understanding why an NLP model makes a particular decision, especially regarding sensitive financial data, is crucial for trust and regulatory adherence. So let's return to the healthcare to emphasize the interpretability. In this example, the system shall ensure high interpretability of its predictions to build trust among healthcare professionals and patients. Actually brings another problem. Imagine a patient with fever, cough, and fatigue. The NLP system might predict this to be as a respiratory infection, but current systems often act as black boxes, meaning the NLP models. The doctor can't see why the system made that prediction. This is a problem because the doctor needs to consider the patient's full history and order further tests. Without interpretability, trust is eroded. So how do we tackle these challenges then? This roadmap outlines our proposed directions for a research. So the directions on NLP ontology generalizability, direction on NLP semantic soundness, and directions on NLP interpretability and human feedback. To improve semantic soundness, one approach is to use contextual embeddings, variations of Bert and Roberta. These help NLP models better understand the meaning of words in the particular context. We also need to fine-tune models on specific NFR data and use ontologies to represent knowledge about the domain. A second approach to semantic soundness is to build NLP models that understand the unique language of NFRs. So basically this involves several steps. First, we need high-quality NFR datasets. Second, we need to carefully annotate these datasets, labeling the relationship between requirements. And third, we should use advanced models like transformers and recurrent neural networks, or even combine them. Fourth, we train these models on our NFR data, or curated data. And finally, we rigorously evaluate how well the model captures semantic similarity. For ontology generalizability, we can enhance ontologies with word embeddings. This would help the model understand the meaning of NFRs. So we can utilize word embeddings techniques such as word-to-vector fast text, a glove to enrich the ontology with semantic and contextual information regarding NFR terms. We could also use text mining to extract relevant terms and relationship and add them to the ontology, making it more comprehensive. Interpretability is about making the NLP model's decisions transparent. We want to create a system where humans can understand and trust the model's output. So this involves techniques to explain the individual prediction and gather feedback from experts. For interpretability, the core idea is to create a collaboration between the NLP model and a human. The model provides its analysis and its reasoning, and the human can then understand and validate the model's output. This leads to appropriate trust, meaning we trust the model when it's right, but we can correct it when it's wrong. So crucially, this process involves a feedback loop, where human experts provide input to further refine the NLP model. There are several techniques to achieve this interpretability, and one way we could do is using a LIME technique. LIME essentially trains local models to explain individual predictions. It perturbs the input, sees how the output changes, and tells us which parts of the input were most important. Overall, this approach helps us understand which input features were most influential in the model's predictions for that particular instance. Another approach is to use sequence-to-sequence technique. The key here is to use variations autoencoders and then analyze how changes to the input affect the model's output. Variational autoencoders aim to create meaningful representations of the input data, which can then be used to generate explanations. With this approach, we can analyze how small changes to the input sequence affect the model's output, providing insights into what the model is paying attention to. We could also use if-then rules to provide global explanation, showing the general behavior of the model and how it makes decisions. The key is to understand how the model selects and applies these rules. The process involves identifying patterns in the data that lead to specific classification. These rules are then propagated from specific examples or instances to more general class-level rules. Overall, this approach selects the best set of rules that accurately represent model's logic. Another crucial decision is building interactive explanation system. This means allowing users to ask why and get detailed explanation from the model. It also involves the model expressing its own uncertainty, how confident it is in predictions. Techniques such as SHAP could help provide these details, pre-prediction explanations. With SHAP, we could implement a mechanism to understand user question related to the model's prediction. So if a question is about feature importance, retrieve and display relevant SHAP information. If the question is about the reasoning, provide a summary based on SHAP values or relevant rules if applicable. So basically, the SHAP values could indirectly provide insight into uncertainty. We could calculate SHAP values for each prediction to show the contribution of each input feature, meaning each word in a text to the model's output. If the SHAP values are small and distributed, it might indicate less clear-cut reasoning and potentially high uncertainty. In other words, SHAP values indicate whether a feature positively or negatively influenced the prediction. Finally, it is essential to have domain experts involved, providing feedback to continually improve models' interpretability. And for that, we need to pinpoint patterns in errors or poor explanation, improve the way explanations are generated and presented, and retrain or fine-tune the model based on expert insights. Thank you for your kind attention through this presentation. I hope this information was insightful. I am open to discussing these challenges and potential solution further. Please feel free to reach out to me via email if you have further inquiries or would like to discuss this research in more detail.